All right, so if you look at your screen now, I'm sharing my screen. So just recap what, just pick up where we stopped. All right, so you should familiar with the red box that you see on your screen. So important for chapter 6 is that you need to identify the point on the object. Okay, so in chapter 6, you need to break the object. For example, the one that on the left hand side top corner here, you need to first step in chapter 6 when you solve a chapter 6 question, you need to look at the object, and then for example this rectangular object, and then you break into um, a few rectangular. All right, so in this case you break into 1 2 3 4 5 6 7 8 16 triangular. Okay, so the process is called discretization. However, in software we call it meshing. Okay, we call it meshing. And what important when it comes to labeling of your point, it should be always anti-clockwise. Yeah, just have a note, because one question will come up from this chapter in your final exam. So always label your point anti-clockwise. So point I, point J, and point M. Okay, point I, point J, point M. Always in this sequence, in anti-clockwise. Later, I will show you one tutorial question. Then you will get some idea how you apply what you learned today. Then for each point, you will have two displacement, U, V and U, U and V, U and V. Okay, and we denote as a sub I means point I. If you sub J means point J. If you sub M means point M. And then in this chapter, another important is the coordinate of the point. Each point on the Cartesian plane, x and y, will give you x and y coordinate. So if the formula that you're using give you xi, means you use the point of x of this point I, right? Xi, yi, and g, xj, yj, and xm, ym. So this diagram is important for chapter 6. All right. And then we also come across okay, then we come across a few equation. All right, we also derive the equation of A and also so on. And there's one equation to find the area of the rectangular given by this equation, 2A equal to so on, x times the differences of y. And then after you get the value, remember to divide by 2 because you need to move the 2 to the right hand side. Then you get the A for the area of the rectangular. Okay. And also we simplify our equation, our displacement equation in this form. So in the form of n times d. And then also we derive equation for strain, and then we arrive at one equation with this one. Okay, so this is an important equation for chapter 6. So strain equal to 1 over 2a equal to beta gamma, and then the displacement. So again for chapter 6, because we are looking at triangular, so we only have 3 points, I, J, and M. UI, VI, UJ, VJ, UM, and VM. Okay, and then we have the strain equation. Okay, strain equal to stress equal to dB times the displacement. So what is D? D is the one that you see on the screen here, the yellow color formula. Remember, this one is, the V here is a Poisson ratio. It's not the displacement V. Don't confuse. All right. And then the D is given here. What is B? B is this one. Okay, this is B. B consists of BI, BJ, BM. So what is BI? Refer to these slides. BI equal to this matrix. BJ equal to this matrix. BM equal to this matrix. Okay, all right. So we will pick up from these slides today. All right. Now, chapter 6, when you derive the element stiffness matrix equation, we are looking at potential energy. All right. Now, for today, always keep in mind, we will talk about potential energy. Okay. For chapter 6, potential energy is our key point when we come to element stiffness matrix. So there's an equation. Your displacement, your potential energy, we use pi p, means potential energy consists of all the displacement inside the system. So this slides, what is important is the second equation here. So potential energy of our system consists of 4 dimensions. Okay, 4 dimensions. First one, strain energy, give you by capital U. Second one is potential energy of the body, or we call it body force. That's why you see a sub B there. First is a strain energy. Second one, body forces. The first one I use a red color arrow. Later, the formula related to the first U, or the strain energy, you will see in red color. And then if the formula related to body forces, you will see green color. The third dimension, or the third component that consists of potential energy in our system, is concentrated load. You still remember what is concentrated load? You have a beam and you have a force. So if you see an arrow, it means concentration load. All right. The fourth one is potential energy of the distributed load, or surface traction. So what is distributed load? Is this one. Okay. All right. And by now, you should know or aware that these two cases, concentration load and distributed load, you can convert them using Appendix D. Just to remind yourself, you can convert into equivalent forces that give you this diagram. In Appendix D. Give you F1, F1x, F2, F2y, F1y, and M1, M2. This one is Appendix D, right? So what is need to take back for today's lecture is this equation that you see on the screen here, this one. Okay, so when you want to derive the stiffness matrix equation, remember we focus on potential energy, and 4 types of potential energy when we derive the stiffness matrix. First one is strain energy. Second one is body forces. Third one is concentration load. Fourth one is distributed load. So if the system don't have distributed load, you just close this one. If the system don't have concentrated load, you just close this one. Then you only calculate the strain energy and body forces. Okay, so it's quite simple concept for today. So in later slide, you'll see a lengthy equation, but it will surround around this equation, right? So just take note that we are going to look at detail of the potential energy for our plane stress element. We are looking at plane stress element, meaning we're going to break, for example, rectangular shape into discretization, meaning we're going to break into smaller pieces of triangular. So each of these triangular will give you energy, potential energy. So what kind of energy, potential energy we consider in our calculation? First, strain energy. Second, potential energy because of the body force. Third one is concentration load. Fourth one is distributed load. Okay. All right.
No
Then I'm going to show
potential.
you.
No.
Yes. Go ahead.
So no kinetic energy.
Again. Your question is broken up just now. Can you repeat your question, Brian? Is it?
So no kinetic.
Yeah, no, because why you mix potential energy and kinetic? We are looking at potential energy dimension now. Do you see it? We are looking at potential energy.
Okay.
Ah, okay. So if just now you mentioned kinetic energy, our object doesn't move in this case. Not so movement, right? Because we start with the rectangular, for example, rectangular object, and then we break our object. In this case, it's just under loading. So under loading, the object doesn't move like a car. Like if you kinetic energy, the equation is mv square, right? You learn in physics. So when we study finite element analysis, we look at very, very small element. So this V is irrelevant. We can say irrelevant when it comes to very small element. All right. So if your element move very fast that you can measure in the term of uh, meter per second, that give you kinetic energy, then uh, is extremely outside the derivation scope already, because we are looking at a small element here. All right. So yeah, take note now. So for chapter 6, when it comes to stiffness metrics, we look at potential energy, PE. Potential energy is the one that inside the element itself. We look at element. We look at plane stress element now. Plane stress, meaning we break a plane. What happened in the plane element, meaning you have X and Y. For example, we take a square or rectangular shape, then we break into half. So we will study a rectangular. And remember when the labeling, for example, this is 1, 2, and 3. When we do labeling, it's always anti-clockwise. When you do labeling, and this is 4. So for example, the first triangular consists of point 1, 2, 3. However, when you define point 2, you need to follow the anti-clockwise direction. You will name triangular number 2 as 0.134. Okay, don't confuse. Don't go turn around and label the wrong point, because uh, when you focus on the direction of anti-clockwise labeling, when you do superimpose later on, okay, when you do deal with metrics, you deal with ticketing number. So when you park the number, if you're confused about the number, the point number, then you'll get the wrong answer. Okay, always have an anti-clockwise labeling. For example, first triangular, you label as point 1, 2, 3. Okay, for element 2 or element rectangular number 2, not rectangular, triangular number 2, you label or you mention uh, triangular number 2 as 0.134 and not 143. Okay, this is just a reminder. All right. Okay, 4 type of energy: strain energy, body forces, concentrated load, and distributed load. Now, potential energy. And for the few slides, you will see a lengthy equation, but remember these slides. Remember these slides, okay? This is the principal idea. All right, don't get distracted by the lengthy equation that you see for the next 3 or 4 slides. Huh? All right, I'll give you the first equation. First one, strain energy given by this equation. You need to triple integrate the the strain, transpose, and the stress equation, and then dV. You need to integrate 3 times to get the volume. Okay, to get the volume. All right. I'm not going deep into how you get this equation, but you just plug and use this equation. So if you need to calculate the uh, potential energy for the system, it consists of 4 components. First, strain energy, you use the red color equation. All right. Then you know that the definition of the definition of stress equal to d strain. You just expand and apply to the equation here. Okay, stress equal to d stress, d strain. You just substitute your stress right in terms of strain. All right. Second one, the green color, because of the body force, you get a negative, again, integration of your volume. Each one of these is one dimension. First one is you integrate x direction. Second one, integrate y direction. Third one, z direction. So three integration give you volume. Okay, what does it mean? So for example, you have x and y and z. So if you integrate y and x, you get this plane. And if you integrate z direction, you will get volume. Okay, you get volume. So this is a potential energy inside the our system. So we have one equation for strain energy. Strain energy have 2 forms. One is in stress term, another one is in strain term, stress and strain. But both of them give you the same answer for the strain energy. Second one, green color one, represent body forces. However, take note, for body forces, there's a negative sign there. Okay. The third one also have a negative. We call it concentration load. You get a negative d transpose, displacement transpose times the p. P is the forces that you have inside the system. All right. This is the focus load force. In this case, we use P to represent forces. And for distributed load, we have a negative again. So integrate, this is the surface area. So you have 2 integration, means you integrate x and y. Then you get the displacement transpose times the displacement times the area. Okay, so you have 3 colors that you see on the screen here: red color, green color, blue color, and yellow color. Okay, so next one, you'll see the combination of these 4. Why there's a negative there? Why negative? Why negative? Why negative? Because potential energy inside system, if we do not do anything on the element, it will equal to 0. So the strain energy plus the body forces, you need to have negative, plus the concentrated load, you have a negative, plus the potential energy, you have a negative. So at the end, you'll get 0 for the system. Okay, so there's a reason mathematics, we need to balance the system. So we have a positive for strain energy, negative, negative, negative for body forces, concentration load, and distributed load. Just take note. Okay, so for the next slides, you will see combination. We will add all these equation. We will write this equation together. All right, and this one is another extension of what you see, because we learn displacement of the system equal to ND form. All right, so this one you can find in the previous slides. The derivation for this one equal to this one. All right. So we combine all the equation together, like I put the color, red color, green color, blue color, and yellow color. And then I will further expand the equation. All right, I'll further expand. So the equation become longer and longer, as you can see. So this one, you can come back to these slides later on. All right, the derivation is not our focus, but if you want to understand, then these are the steps. So we will arrive at this equation. So as you can see, I highlight with a light blue color. Light blue color means that this is referring to total load on the element, because this one, the red color, is the U, which is energy. Let me refer the strain energy inside the system. Okay, this is U, while these three are the loading on the system. Okay, loading on the system. First one, body forces, the green color body forces. This one is the concentration load. This one is the distributed loading. All right, then we arrive at the simple form. All right, we just combine this green color, blue color, yellow color into a white color F, because we can factor out this one in the equation. The green color, blue color, and yellow color have the D transpose. So we just factor out, and then we combine this green color that I highlight with the symbol here. So the combine of green color, this one, and this one, we write as a F, as a loading of our system. Again, we will do differentiation, derivative, means differentiate. We will differentiate this whole equation with pi, with a nodal displacement. You see the mathematics equation. You will differentiate, means you do the dy over dx. In this case, your y is this one. Your x, in this case, you will use displacement. Okay, you use displacement. So when you do derivation, dy dx equals 0, mean to get the balance point. All right. So you rewriting, you get this form. And previously, since chapter 1, we always mention F equal to KD. So F equal to KD, if you compare the form, this one, and this whole form, F equal to KD, if you compare the orange color and this formula, this is your K. Because F equal to KD, you have your D already. So the remaining one is your K. So this is our focus for the first session of our lecture. So our K equal to triple integration to get the volume of B transpose. Okay, So we already know what is our B. We already know how to find our B. We already know how to find our D, and the triple integration of our three axes to get our volume. So if an element with a constant thickness T, then we can take out one of the integration, replace with thickness, and then the remaining one is your area, because thickness times area, you get volume. Okay, then how you get the area? You just need to consider your dy and dx. So this is your z. This is your dz. So in this case, we have a constant thickness of t, so you just replace your dz dimension with t. Okay. So when you do integration, meaning you can replace dx, when you take integration of this dx dy, this combination of, because you know that this is constant value, so you integrate your dx dy, you get a. So you can write your stiffness matrix K for plane stress element as TA or area, B transpose D, and times the B. We already show you how to get B. We already show you how to get D. So transpose is a matrix function. I already show you how to get the A, the 2A equal to something, the equation. So from there you get your A. Thickness will be given. So basically you can solve what is your K. Okay, just to conclude what is important for today's session. K equal to TA B transpose DB. Okay, important matrix equation for your final exam. Okay. All right. So the rest you can find in my slides. What is B? What is D? What is A? I show you since the beginning of this lecture. I already show you what is B, what is D, what is A. So what you need to do is substitution, and then you do the multiplication of matrix here. So I already show you the online tools. So you are allowed to use the online tools to help you to do the calculation. All right. The rest is just a side note. So remember, when you get at the end, your K form or your K matrix is in 3 times 3 matrix. Okay. Your K matrix is in 3 times 3 matrix at the end. The first one is K1II. Second one is Kij. The third one is Kim. All right, remember we are talking about 3 points in rectangular. I, J, M in anti-clockwise. Okay, in anti-clockwise. So what does it mean? It means that each one of the K, for example, Kii, you need to calculate based on the equation that are given on the screen. It's a very jumbo matrix actually. So for Kii itself, that's why you see a square matrix symbol around the Kii. So Kii, each one of it, you need to calculate using this equation. For example, if you look at Kii on the first K matrix number given by this equation, they'll use TA, thickness thickness is given. Area you calculate. BI, the first, if you want to calculate KII, you use BI transpose, then DBI. If you want to calculate the second one, KIJ, you use the thickness. Area, you use BI transpose DBJ. Okay. Now the third one, I'm going to ask question each one of you later. I'm going to ask what is this one, what is this one, and what is this one. So typo error here. This is JI, KJI. Later I'm going to ask each one of you, give me the equation of this one, this one, this one, this one, this one, this, and this one. So I'm discussing about how to get KIJ, how to calculate KIJ. KIJ give you thickness times area, BI transpose, D and BJ. And then the third one, KIM. KIM equal to thickness, area, BI transpose, T is a transpose, D and BM. So what is the differences? What is the trick here? As you can see from the PowerPoint slides, the first notation give you the first matrix B. Second one give you the second matrix I. Same with this one. Second one, KIJ give you BI transpose D BIJ. K, the third one, if your first one is I, the first one is I. If the second subnode M, the second is BM. Okay. So just recap. I'm going to ask question later on. So what is this B and M about? I'm showing you just now. This is equation for D. And I'll show you what is B. Okay, this is B. How you calculate B? Your B, you have three number there for B matrix. You need to calculate BI, BJ, BM. BI give you this matrix. You just substitute beta I, gamma, and so on into here. Area, this one. Area equation, this one. Okay. Area equation, 2a equal to all this point, xi and then yj minus ym, so on. You get 2a. After that, you move your 2 to the right, you get area. Okay. After you get the number here, divided by 2, you get the area. Okay. So alpha I, alpha j, and so on. I'll show you on the screen here. All right, I'm going to ask question now. Let's just see whether you understand or not. Okay. Okay, let me correct that. This is A. Typo error in my slides. Okay, I'm going to ask question now. All right, I'm going to ask Ashmal, the first one. Ashmal, give me equation for this one. This is asking. Yeah. Okay, later I give you like maybe 1 minute to sort it out. Sue, maybe this one. So you give me the equation for KJJ. Brian, you give me this one. Brian, you give me this KJM equation, how you calculate this one. And Chia, you give me how to calculate KMI, right? All right. Ashma, if you're ready, you can give your answer. How to find KJI?
KPI equal to TA
Mhm.
times BI,
BI,
BJ,
BJ, what transpose?
yeah, transpose,
D, and then
D, BI.
BI, correct. Okay, means that you understand. All right, Sue, what is, how you calculate KJJ?
Thickness times area
Mm-hmm.
times Bj transpose times
Mm,
D times
mm,
Bj.
correct. Brian? Brian, how to get this? How do you get this matrix?
That T,
T, A, and then
BJ,
BJ transpose D, and then
BM.
BN. Correct. Okay, good. Chia, how you get this one? KMI,
EA
TA,
get EM
BM transpose D, and then
EI.
BI. Correct. All right. Excellent. All of you know what is the concept, how to get the K in this on these slides. Yeah? Okay, excellent. This actually free mark. Once you understand how to park the numbers or substitute the number, this actually is a free mark. The process is the same. All right, good. Again, this is a very big matrix. After you get the number, you get a very big matrix. Then after that, you put in a f equal to kd equation again, small f equal to kd. So you're going to get a 6 times 6 matrix normally for plane stress analysis. 6 times 6. Why you know 6 times 6? By now, you look at the displacement, you already know the form of your K matrix. Because your form, you have 3 points. Each point give you 2 displacement. U1, V1, V2, U2, U3, V3. So if you do the ticketing number, U1, V1, and so on until V6, you have 6 number ticketing number on the top and 6 number on the right when you write with your pencil. So you have a matrix of 6 times 6, and each point will give you 2 forces for beam. So F1x, F1y, F2x, F2y, and so on. Okay. So basically, you are familiar with this form, right? We still back to F equal to KD. So you solve for the D, because K is all the constant value that you plug from, you substitute from the diagram. You calculate the coordinate, the beta value, and so on. You solve for the K. After you solve for the K, you have the complete K matrix already. Then you look at the bounding condition. You can find what is, basically you have 6 equations here, and then you use bounding condition to close either 3 row and column here, then you solve for 3 equation, then you solve for the force, just like what you did for the previous lecture, previous chapter. Okay, so these are the equation that you see this morning. Again, 4 dimension, strain energy, potential energy for body forces, concentration load, distributed load, and so on. So the red color is the first one, strain energy. So just now, we already proved to you that K equal to this equation. And you can write the first term of the strain energy in the equation that you see at the bottom of your screen here. So this is in the quadratic form. U equal to half displacement transpose K and D. K is this lengthy equation, right? But you can substitute the K with this equation that you learned just now. Okay, K is this one, right? So use back this equation to find all the K inside here. Later you will see one example in tutorial question, then you get the idea. Okay, the U equal to this one. Then you do the normal solution for capital F. After you solve for the displacement, you write the equation in capital F, global dimension, capital F, K, and D, and you solve the remaining unknown. Okay. So this is the diagram that you derive from normal equation. First one, you have your y and x. Then you have your x prime, y prime axis, with referring to your triangular. So you start your x prime, y prime axis start with point I, which is normally on the lower left corner of your triangular. All right. Now, no matter how the triangular rotate, we always pinpoint the lower corner of the rectangular triangular. Sorry. Okay. We always pick the lowest corner of the element. So this one happened when you solve using ANSYS of SolidWorks. When you do meshing, the software also will pick the lowest corner first. Okay, let's say you solve a rectangular problem. You always start with the lower corner and then you solve for the sometimes solve for this element. After you solve for this element, you proceed to second element. Then it will combine the result and project the results to you. This is how the software or mathematics solve solution. Okay, then you solve for the D, F element, and so on. Okay, these are the important equation. And I show you the T matrix. If you need to find the displacement, this is the local. Still remember, we use D prime to represent local. And this one is the global. So every time we look at the x and y and x prime, y prime with the angle, as long as you have an angle, you involve cos and sine. I remember what is theta. Theta always refer x to x prime. Okay, refer to x to x prime, where positive angle will always calculated from x direction, or you can say as an anti-clockwise direction in this case. Just a recall, this is you already learned already. All right, then you put in T form. So this is just labeling for you. I just label the side for you. So same, the first represent UI, VI, UJ, VJ, UM, and VM. So these are the parking ticket that you should know how to issue when it comes to T matrix. Okay, T means it's a conversion that you use to convert the X and Y axis with the angle. Right? So don't confuse. This is just a very light equation that you do conversion, especially when you do when you need to convert it back to global axis, right? Or in a more simpler word, it means that every time you see the x prime, y prime, x and y, then for sure you need to use transpose matrix, a converter that convert d prime in and d. D prime equal to TD, or if you need to convert the forces on the x prime axis, then s prime equal to the converter factor or the T matrix times the force. And if you need to calculate the K, what you need to do is that you can see the third equation in yellow color. K equal to T transpose, means you take this one transpose times the K prime and the T. So this one I think asked by Chia before. So the derivation of this equation can be found in my PowerPoint slide, chapter 3D. Chapter 3D PowerPoint slides and the video also. So I explain how you get this when we discuss how to change H to X prime axis with a loss of colorful arrow that we derive in chapter 3. Okay. All right. Okay, then you continue with the other steps like what you did in the chapter 4 and chapter 5. So you assembly, you solve for the unknown. Okay, so we go for a short break, then we look at one example. Okay, we stop the recording.